Hello there, my name is Ray Watkins here, and I'm going to be presenting our CAP number 2 assignment, Fate of Lactate. So the objectives of this presentation are a couple things here. First, I would start off with defining, what is lactate and actually what it isn't. Next, also, too, we'd like to look at how lactate is used in the body. So lactate utilization, especially through what's called the Cori cycle here. Next, we'll look at the effects of lactate accumulation and see how the body responds to that accumulation of lactate in the blood and in the muscles. And then lastly, we can look at how exercise intensity and actual specific training can affect lactate utilization in the body. So to start off, we're going to talk about what lactate is and what lactate isn't. Lactate and lactic acid are not the same thing. Lactic acid is the immediate byproduct of anaerobic glycolysis, whereas lactate is formed from lactic acid here. So when we have lactate formation, what happens is those non-oxidized hydrogen ions from lactic acid combine with pyruvate there, and that combination, catalyzed by an enzyme called lactate dehydrogenase, actually form lactate. So it's something where lactic acid is one thing, lactate is a formation of anaerobic glycolysis there. And once we get that lactate, next we got, a crossroads or two different paths that lactate can take. First, it can be diffused into the interstitial space or going into the blood for buffering and removal, which are two things we'll discuss a little bit later. But then also can be used as an energy substrate. So this is something where it's very important to think of lactate as not a waste product, but it's something where it's a byproduct that can be turned into something to be used for energy by the body. So the way that the body uses lactate for energy is that it uses this Cori cycle here. So what happens is when we get anaerobic glycolysis performed in the muscle by high intensity actions right here, we're going to get this glycolysis byproduct of pyruvate. Now, because of the intensity of that exercise, oxygen is not readily available to bind with pyruvate. So what happens is it then gets turned into lactate, like the formation process we described earlier here. This lactate then enters the bloodstream, and via the bloodstream, it gets transferred to the liver. Now, while it's in the liver here, this liver accepts the lactate and does two different things. In this process of gluconeogenesis, it can produce the glucose in its simple form to be used for energy again, or it can convert this lactate into glycogen or stored glucose in the liver to be used later for energy. So with this cycle, once we get to this point, that glucose that's been converted from lactate will then go into the bloodstream and can return to the active tissue for subsequent use of activity. So this is that process, again, like we were saying, is using a byproduct as an energy substrate. So it's not a waste. It's basically the recycling of lactate to be used again for energy, remaking glucose. Now, this is very dependent on intensity of exercise and then also duration of exercise here. So when that intensity or duration or both of exercise increases beyond the speed that the Cori cycle can handle, we're going to get lactate accumulation. And this is where the body has three different mechanisms to try to go ahead and deal with that lactate accumulation. So this is where we talk about buffering. So the concept of buffering is basically how the body handles an acidic environment. So it's the pH level balance. It's a very sensitive balance, and the body has different ways to go ahead and try to bring that environment, whichever be in the blood or the muscles or so forth, into as much of a neutral environment as possible. So the first way that the body buffers this lactate here is a chemical buffering. So through certain substances like sodium bicarbonate, phosphates, blood proteins such as hemoglobin, so forth, they are available to buffer that those free-floating hydrogen ions there and bring the pH to a normal level. So after that first stage of buffering, the second, stage here that the body uses is pulmonary ventilation. So what it does is the body uses ventilatory rate and to increase alveolar ventilation. So that's where the exchange of oxygen and carbon dioxide happens within the lungs in the body here. And through that process, these carbon dioxide can bind with those free floating hydrogen ions and help bring the pH down in the body. So we actually blow off some of this acidity through carbon dioxide production. And then lastly, what we have is the renal buffering system. So this is going to be happening in the kidneys here. So in the renal tubules of the kidneys, they secrete ammonia, and then ammonia takes these free-floating hydrogen ions, which is causing this acidic environment, and shuttling it to the urine and eliminating it from the body. So it's kind of the last exit door for this acid buildup here. And also through the kidneys here, we can reabsorb some alkaline chloride and some bicarbonate as well to help with further buffering. So there's three main systems that the body uses when the Cori cycle cannot keep up with the accumulation of lactate. Now we're talking about this lactate accumulation here. There's certain effects on the body that happen. So as we discussed, as exercise intensity increases, lactic acid production and lactate accumulation increases. So there's a direct relationship. And with this increase in lactate, we get these hydrogen ion concentration in the blood that increases. So then the actual pH of the blood decreases, so it becomes an acidic environment. So that's going to be acidosis. The thing with this acidic environment that it can affect the muscles, and the muscles can't perform optimally in this acidic environment, so they tend their ability to maintain force and to produce muscle actions decreases, and even to the point where extreme acidosis can bring certain symptoms of nausea, dizziness, vomiting, and overall cessation of exercise. So now what we look at here is going to be the relationship between exercise intensity and blood lactate levels. So if we're looking on this graph here, we can see on the bottom here on the x-axis is the running speed, which would basically indicate our exercise intensity. And on the y-axis there is going to be our blood lactate measurement here, millimoles per liter. As we can see, moving here across this line, we're going to have a steady line or a steady relationship between running speed or exercise intensity and blood lactate levels. So what that is that's not the failure of the body to accumulate blood lactate at these intensities, but what it is, it's the body's ability to match that accumulation with the removal of lactate. So as lactate's being accumulated, lactate is being removed or utilized by the body. Now, this process is at a steady state, so we won't see a rise in blood lactate, but this usually goes until about 55% of a regular person's VO2 max or exercise intensity. And then that's where we get into this onset of blood lactate accumulation, or also called lactate threshold. This is the point where accumulation is going to rise above the body's ability to remove the lactate, and we're going to get this exponential rise in blood lactate. So this increased rise in blood lactate can lead to those symptoms that we talked about before, where we get decreased muscle force action, and then also leading to cessation of exercise. Now, as exercise scientists, we like to think of cessation of exercise as a negative because we want to increase performance here. So what has been shown is that blood lactate levels actually have a relationship with training adaptations that are made. So what has been shown here is that aerobic training adaptations allow for a higher relative onset of blood lactate. So if we're referencing this similar graph that we had here, we can see that both the blue and the red lines here have a similar steady rate of lactate accumulation and lactate removal. But then this blue line here, which represents the before or untrained subject here, we're going to hit our lactate threshold and we get that exponential rise in blood lactate levels. But due to aerobic training, what can happen is we can increase the body's ability to remove or remove lactate and then also to buffer lactate so that that exponential rise comes later and when it comes to relative exercise intensity. So even highly trained endurance athletes can achieve this lactate threshold or onset of blood lactate accumulation from 55 all the way up to 80 to 90%. So you can see it's something where how through training the body can be more efficient at dealing with these byproducts here and using them as energy and increase performance. Now, what I wanted to do is look at some of the specific training adaptations that can affect onset of blood lactate accumulation here. And these are the things that happen during aerobic training here. We get increased cardiac efficiency. So increased cardiac output, increased capillary density. So that's going to allow the cardiac system to help improve aerobic performance. Also, the pulmonary efficiency as well. So, how the increased AVO2 difference or the diffusion of oxygen into working muscle cells, and then also increase of the hemoglobin percentage. And that's that, protein that in the blood that can help bind with some of that acidic environment there. That becomes more efficient. And then also looking at the mechanical efficiency or basic, I guess, running mechanics or, genetic endowments or running economy, those sort of things. So these three things, cardiac, pulmonary, and mechanical efficiency increases help shift that onset of blood lactate into a favorable position for an athlete. So to sum this up or kind of land this plane here, I wanted to go over these three concepts here of what lactate is and what it isn't. Lactate and lactic acid are different, and lactate is definitely formed by that hydrogen ion and pyruvate coming together, and it's catalyzed by lactate dehydrogenase, and then it has a chance to be reused for energy through the Cori cycle here. Now, what's dependent for that response of lactate is going to be the intensity of exercise here. So at a steady rate from 0 to 55%, you get that steady rate removal, but then sometimes we're going to get that accumulation when we start working at intensities higher than that. And that's when the body has to respond by with its buffering actions. It has its chemical, pulmonary, and renal buffering actions. But any excess of that leads to an acidic or an acidosis, and there's negative effects within the body. So, and then lastly, looking at training intensity, like we said too, anything really over about that 55% is going to bring that onset of blood lactate accumulation. But through training, other specific adaptations, cardiac, pulmonary, or mechanical adaptations, someone can increase that onset of blood lactate accumulation up to, it's been shown to 80 or 90% of someone's VO2 max. So I hope this helps you understand the fate of lactate from its beginning to its utilization and to its removal. Thank you very much.